Greetings, my friends and fellow Earthlings, and welcome to Ask an Astrobiologist, the show where we celebrate the science and celebrate the scientists involved in our quest to understand the nature of life in the cosmos. I'm Dr. Graham Lau, also known online as the Cosmobiologist, your host for the show, and we're brought to you by NASA, Astrobiology, and SegaNet.org. And this is going to be the last episode for 2020, but I promise it's going to be really groovy. I'm so excited. We'll be talking about Titan, about the upcoming Dragonfly mission, and a bunch of other stuff when we ask an astrobiologist all about that. But first, we have a few of our fun things to get through, like our contest. Earlier in the week, last week, NASA Astrobiology sent out a tweet asking who discovered that strange moon of Saturn called Titan. And we had a whole lot of correct answers, and it's pretty easy to Google search that, I guess. But our winner is John Beal at Darkwalker168 on Twitter, who not only said Huygens, which is correct, but also said, can I go to Titan too? It's my favorite moon. And it is a really cool moon. For those history buffs out there, you might know that Titan is the sixth moon we discovered in the universe. Outside of our own moon, which was one, and then the 4 Galilean satellites of Jupiter that Galileo found, Huygens was the next person to find a moon. And at first, Titan was just called Saturn Moon, Saturni Luna. It was the only other moon that we knew of, and so it was just Saturn Moon. Eventually, we found many, many, many more, and so we had to have a better name for it. Also, as usual, we love to point out the people who take the time to share about our show, to share about our featured guest for the month, to share information about the topic, and just get involved in everything Ask Astrobio. And so this month, our ambassadors that we want to just give a huge shout out to are Anirudh Mahanti at Strayologist on Twitter, Marianne Denton at AstroLimno on Twitter, Denise at AstroBioDNZ on Twitter, and then someone called T at Tiramari _ on Twitter. Thank you all so much for sharing the show, for getting involved, and as always, for asking an astrobiologist. Now, I'm going to introduce our guest for this month. Dr. Melissa Trainer is a research scientist at NASA's Goddard Space Flight Center, and she's also the deputy principal investigator for the upcoming Dragonfly mission to Titan. So, Dr. Trainer, hello and welcome to Ask an Astrobiologist.
Hi, really happy to be here.
Yeah, it's so great to have you on. I'm really excited just to nerd out over Titan and Dragonfly a little bit and learn more about this mission, what your role is with the mission, and the science that we're going to learn from it. I do want to remind the audience to ask your questions in the chat at SegaNet.org or on the NASA Astrobiology Facebook page. We'll get those into the queue then for Dr. Trainer after she and I have a small conversation here first. And Dr. Trainer, I always love with our guests, since a lot of our audience are undergraduate, maybe high school students, maybe recent graduates, they want to know how to become astrobiologists, what our pathways are to get to where we are in our careers. And so I'm wondering if you can share with us maybe your science story, your superhero science origin story for what really brought you to where you are currently in your career.
Sure, happy to. It wasn't a plan, I should say. I wasn't one of those kids who said, I'm going to work at NASA someday. I always loved NASA and loved planets, but probably like a lot of young people, maybe especially in the 80s, I was mostly only aware of astronauts and the space shuttle program. And that probably made the biggest impact on me when I was a kid. But I always loved math and I love science. And so I followed those interests. For example, through college, I majored in chemistry, partly because I also loved being in the laboratory and I loved like mixing things up. And so as beautiful as the night sky is, I was really a lot more drawn to hands-on laboratory work than necessarily observational astronomy, for example. So I was graduating chemistry. I knew I didn't want to get a job yet. I knew I wanted to keep going to school. And so I started trying to figure out what kind of research really interested me and really excited me for going to graduate school. And I ended up really drawn to the study of atmosphere and atmospheric chemistry, but more so for Earth, right? That was my original thought. I had these like visions of I'm going to climb mountains and measure ozone and do all those kind of measurements. And so that brought me to the grad program I went to, which was at University of Colorado Boulder. But when I started looking for projects and people I wanted to work with, the professor and the group I was most drawn to, the Available project that also really suited, I thought, my interests and my strengths, was studying the chemistry, not of the Earth's atmosphere, but of Titan's atmosphere. So sort of a little bit of a just grabbing an opportunity that I had to do something I hadn't necessarily planned on, but still found really interesting. And that's sort of the theme when I think about how I got to where I am today. That's sort of the theme. So I did all my graduate thesis work studying Titan as well as the early Earth and kind of the connections in atmospheric synthesis and the role that might play in distributing complex organics kind of all around a planetary system. And I did a little postdoc work studying Mars polar caps. And that was right around the time that methane observations of Mars were just starting. And there was a lot of interest in that. So again, just tried to do some lab work, thinking through what are some possible mechanisms of trapping and re-releasing methane. The spoiler alert is we didn't find any. I didn't find any in that particular project, but sometimes a null result is still really, really valuable. And then we're kind of ready for the next step and trying to figure out what I was going to do. And I think I had sort of always assumed I would, go into academia and try to get a professorship. But again, like sort of out of cycle from that, before I could even do all that work, this job opportunity at Goddard popped up. And I ended up meeting with the people who were hiring, coming out to visit, giving a seminar. And it was yet another one of those, this is not necessarily the thing I planned to do, but this is really exciting and this is really interesting. So I'm going to give it a try and see how it goes. And that is how I got to Goddard. And then the group I joined is one that is very involved in missions and in building instrumentation for missions, such as the SAM instrument on Curiosity. And through working in that group and working at an institution, especially that's really based in mission work, I'm proposing and executing planetary missions is sort of what led me kind of in the business and set me up to be part of the Dragonfly team.
Oh, that's wonderful. I'm super jealous. It sounds like you've had your hands on so many different awesome missions and concepts as well, including the Titan Mare Explorer and all these things that kind of coming up to this culmination of exploring Titan. One really cool thing I learned from you in preparation for this episode was actually going to lead into our current field site challenge we just released yesterday. On Twitter, we asked people to guess the location of a certain picture relevant to the exploration of Titan. And that picture was an image of linear dunes in the Namib Sea in Namibia. And I can't help but hear David Attenborough's voice going, the Namib, the way that he would say it so poetically and beautifully when he would talk about the Namib. Our winners for that contest are Lloyd Jolly, Cass Marion, Sri Likya Chowdhury, and Eduardo Aco Perez. So thank you to all of you who competed in that challenge as well and realized this was Namibia. And I wonder if you can speak to that, why Namibia is so important for our explorations of Titan.
Sure. So one of the features of Titan that is really fascinating and compelling to think about and is part of our target when we go with Dragonfly are these dune fields, these equatorial dune fields that are present and sort of wrap around the moon. They're really noticeable from the images that we have of the surface from Cassini. And the formation and the processes that lead to those dune fields and kind of the shaping and the spacing with these wide interdune flats where we think you have access to the bedrock, which on Titan would be water ice. As well as then the sort of pile up of dune particles. The way those are formed, we expect would be very similar to how some of the dune fields on Earth form. And so that image that you showed and that Namibia sand sea is an analog for that region on Titan. But what's so cool about Titan is that it's totally different materials. I sort of hinted at that already, right? Instead of having your exposed bedrock be some kind of, silicate-based rock, it's water ice, which is the crust of Titan. And the dune particles that are piled up are expected to be made up of organic carbon, organic molecules. And exactly how those particles form, we're not entirely sure. But that's part of what we want to learn more about.
That's great. And that leads me then to Dragonfly and learning more about it. So I mentioned earlier, Titan was the first moon of Saturn we found, and we now know of lots more. Titan's surface is very cold. It's like 20 Kelvin warmer than liquid nitrogen. So it's pretty cold. And yeah, there's this methodological cycle instead of a hydrological cycle. And there's methane going into the atmosphere and breaking down and making all these other things through photochemistry. And there's like this raining gunk coming down to the surface of Titan, which is very cool. I wonder if you could then set up for us maybe the brief history of exploration of Titan. I know we had one mission land on Titan, and what really leads us now to want to send Dragonfly there? I've heard this question a lot. Why are we sending Dragonfly to Titan?
Sure. So you've talked a little bit about the original discovery of the moon, just looking from Earth through telescopes, and that's probably just because it's large, right? So it was one of the earlier moons that was able to be observed, and there were studies from more advanced studies earlier last century using telescopes that led to the discovery that Titan has an atmosphere. And in particular, that there's methane in the atmosphere. And so that sort of already kind of pulls Titan out as unique among all the other moons in that it has a substantial atmosphere at all. And then with flybys from, for example, Voyager, we got some really good images of what Titan looks like kind of from the outside. In the visible, it's like this hazy orange ball. It looks kind of like a marble or like this fuzzy ball. But spectroscopically, we see that's related to as you said, the methane in the atmosphere. But energy coming into the atmosphere and photolyzing that methane leads to very complex chemistry. And so the particulates that give it that hazy orange look, that right there is sort of the first clue. Titan's got something really interesting going on. These are organic particulates made up of chemicals that are formed through that process, and they condense out and they make this haze, and that completely obscured the view of the surface. But was the first hint that there's some really, really interesting carbon cycling going on, and the potential for those organics to be very complex organic species. So it wasn't until we got there with Cassini, the Cassini-Huygens mission, that we were able to actually see through that haze layer and get an idea of what the surface was like. Before that, there were a couple different hypotheses. One was that maybe the surface was covered in just a whole ocean of liquid ethane, with the thought that ethane would be a major product from the photolysis. You get enough of it, it's all going to just condense out, and maybe there's liquid ethane everywhere. They're not totally sure until we got there with Cassini-Huygens. And so Cassini was the Saturn orbiter, but it dropped the Huygens probe off. Huygens fell through the atmosphere for several hours, and then it lived on the surface, actually, which wasn't necessarily expected or planned for because we didn't know what it would land on. But it survived on the surface for about 70 minutes. But what it did while it fell through the atmosphere, it took images of the surface, and as it descended down from those images, we could see sort of evidence of really interesting topography, river channels. It landed in what looks like a plains area. And it also took measurements of the composition of the atmosphere while it fell down. So the methane and the nitrogen, as well as some of the trace species and isotopic ratios of some of the major species. And also things like pressure and temperature, kind of giving us the profile, winds, all the way down. So that's sort of our one data point of really understanding what Titan is like all the way down to the surface. Also looking back up at the haze, at all those particles, to get an idea of sort of what are they made of, what shape they are, how dense are they down to the surface. And then since it survived on the surface, we have really great images taken from Huygens sitting of what that area of the Titan surface looks like. So those 3 hours was an immense leap in our understanding of what Titan's like. But luckily, Cassini kept coming by Titan over and over, right? So over 100 flybys of Titan. And from that, we have learned so much too about Titan, as a planetary system, basically, right? As I always refer to it often as a planet, because other than the fact that it orbits around a different planet, it acts like a planet. So the Cassini orbiter gave us views of the surface in different, channels of light that could get through the haze, the absorption of the methane or the haze, different visible and infrared lines, as well as using radar to get ideas about the topography, what the surface is like. And from that, we can see, Titan is a fascinating place. You've already hinted at a lot of the cool features, things like the methane cycle that acts like the hydrological cycle on Earth. We have observed clouds. We've seen evidence that it does rain, sometimes on Titan, except there's river channels. Cassini discovered near the North Pole a whole region of seas that are primarily methane and ethane seas. So Titan's the only place in the solar system you could go sailing other than Earth, if you could stand the cold.
That's awesome.
And there's, we mentioned mountains. It's been speculated that there might be cryovolcanism. So the ice shell acts sort of like bedrock does on Earth. And then for Titan, underneath that, there's a subsurface liquid water ocean. And so it's thought that it's possible that you could get eruptions of this liquid water out onto the surface. And despite the fact that Titan is so cold at the surface, if you have enough energy, either in that kind of eruption of cryolava, or, for example, a big impactor comes in and makes a big impact crater, if you get enough energy in the system and you melt the water, you have some liquid water present on the surface, it could last for 100, 1,000, maybe even 10,000 years, depending on how much energy it takes. It still takes a long time to cool off. So when you put this all together, what we've learned from exploring Titan is that you've got this location where we have sunlight coming in, potentially other energy sources. We have water, definitely liquid water, below the surface and sometimes on the surface. And we have more, organic carbon than you could possibly need, right? It's sort of the opposite of what we're doing on Mars, where we're looking for, just a few molecules, preserved in rocks, right? And Titan, it's like it's organic carbon everywhere. So we have complex organics. So what happens, right, when you have all of those things together? So what happens when you've got this super rich organic chemistry taking place in the atmosphere and it's depositing everywhere, it's depositing all over the surface? You suddenly have an impactor come in, you create a melt pool. Now we have all this organic molecules and they're sitting in water and they're sitting in there for thousands of years. You have a lot of hydrolysis reactions, other reactions can take place. Can you start to make the types of molecules that we think of as important for biochemistry? Can you start to make things like amino acids and nucleobases? And if you are able to make them in a synthesis step, do they continue going on? Do you make any, oligomers of those things? What kind of, how far can an abiotic synthesis or this kind of process take you in terms of complex chemistry, sort of on the route, like what we think of as prebiotic chemistry? So those are some of the big questions that are part of the Dragonfly mission. Those are the big questions I have in going to Titan and exploring Titan. And then in addition, we're able to make like very specific measurements maybe about some of the chemical composition of some of the surface materials that we encounter, but we can do so putting it in the context of the whole area that we're exploring in, right? So also spending time on the surface and making measurements, understanding the environment, understanding sort of the meteorology, and kind of piecing it all together. What does it mean to have a place like Titan that has all the ingredients we think of are important for life? And how does that all kind of come together as a system? And what can we say about what that means for what we think about habitability? What makes a place habitable, for example.
Interesting. Yeah. So it seems like there's a lot to learn just about planetary processes in general and atmospheric processes by going to Titan and exploring. I'd not read before about this potential for liquid water to come up to the surface or impact or to leave it on the surface for a long period of time. So that presents a really interesting potential for an oasis or a refuge, if you will, for a potential life if it's there. So how would Dragonfly then specifically as a mission help us to understand this? What kinds of instruments will we be taking? What kinds of measurements will it give us?
Yeah. So one of the big features, and I'm going to point to the Dragonfly in my background since I'm broadcasting from Titan. Of course, one of the key features of Dragonfly is that it can go to more than one location. We call it a relocatable lander. So we're able to visit multiple types of locations. I've talked about dunes and organic dune fields, and now I've talked about this potential for there to be, we know there are impact craters, and that at some point in their history, they would have been liquid water, frozen over now, but our plan is to visit one of these impact craters and look for evidence of this type of chemistry. So the way that we'll do that, we'll measure the composition of the surface in several locations and be able to compare it and kind of understanding a processing history. We do that a lot of the way, very similar to how Curiosity rover makes similar measurements on Mars and looks for organic materials on Mars. So we'll drill into the surface. We have a cryogenic drill, and that delivers a sample to a mass spectrometer. So using the mass spectrometer, we'll look for different types of organic molecules, identify different compound classes by comparing like we find in the dune sands to what we might find in sort of this frozen over impact deposits. We can make some inferences again about the type of processing that may have taken place. We have two different ways to measure surface samples with the mass spectrometer. One involves shooting in the laser, which is sort of our first look, and that helps us get some of the larger molecular weight molecules. But then we also have a gas chromatograph. And using that approach, and again, this is something that has been done on Mars, we do what's called derivatization. So we use a chemical reagent and mix it with some of the molecules that normally might not, if you heated them, go into a gas flow, but we make them more volatile, and then we can send them through our system and measure them in the mass spec. And that includes things like amino acids. And it also gives us the capability, we're carrying a special separation column with our gas chromatograph that lets us look at chirality. So that's sort of the handedness of molecules. That's really, really important biosignature for our biochemistry as we know it on Earth. And so that's something that we have the ability to look and see if there's a big enhancement in one chirality or another. So that's very focused on the chemistry measurements. But we're making tons of other measurements as well. Again, to really understand this whole planetary system and learn more about planetary processes as well, and put the chemical measurements in context. So, of course, imaging. Lots and lots of imaging, right? We couldn't go to Titan and fly around Titan without sending back lots of pictures. So we have a whole suite of cameras that lets us get panoramic views of where we're landed, forward and down-looking views. We have a microscopic imager that'll let us see in much finer detail the types of surfaces, the types of materials that are there, as including the area where we will drill if we decide to take a drill sample. And so from piecing together all of those, we can learn a lot about the geologic history of the different landing sites that we're in. For example, to learn a lot more about how those dune fields are formed and transformed over time. We're also making meteorological measurements, so things like temperature, pressure, wind, looking at methane, humidity. We have the ability to make seismic measurements, a seismometer, for example, to learn more about the interior and try to constrain the distance maybe from the ice crust down to that subsurface ocean, and understand a little bit more about interior structure and how that interior might connect with the surface and what implications that could have for were there, let's say, potential life in that deep subsurface ocean. We also have gamma ray neutron spectrometry measurements, which are which are really useful. We are able to get a bulk elemental composition of every landing site that we're at. So it sort of tells us, what major elements, of course, carbon and hydrogen and oxygen will be important ones as we're landing on sites that have different amounts of water ice or maybe organic molecules sort of layered on top, almost like a soil or layering on top. But if we land in an icy spot, we might also see evidence that there's a lot of salts, chlorine and sodium and different cations and anions. If they kind of pop up in those measurements too, that could tell us a lot about the history of that area. And again, potential connection maybe from the interior ocean. And that also helps us classify site to site. Is where we're sitting now very similar to where we were last time? And if so, do we want to, is it worth drilling and taking another sample, or should we keep continuing on to find kind of a new geologic unit?
So very cool. Yeah, I'm just like smiling widely over here, just thinking about Dragonfly and what's possible. I do have a couple of rapid fire questions for you actually too. I gave a talk last week at the Denver Museum of Nature and Science. And of course, children always ask the best questions. And I had a bunch of kids ask questions that I had no answers to. So a quick one, how big is Dragonfly going to be?
Okay, so Dragonfly, you want to picture the scale is kind of like a Mars rover, right? So this is not a teeny little drone. This is a serious spacecraft because it's got to carry that whole payload.
Mm. Okay, so maybe like a small, like a Mini Cooper kind of size.
Yeah. Something like that. Maybe, I mean, it'll have its own little dimensions, but it's, hundreds of kilograms.
Very cool. Another question that I'd had, why did we choose to put on 8 propellers on the spacecraft? Why not 4 or just 2?
Well, by having 8 and having them arranged the way we have them, where it's really 4 locations with 2 each, that gives us a little bit of redundancy. So if one of those rotors were to go out, for example, we could keep flying in a very balanced and controlled way.
Oh, very cool. And then another question. So obviously there'll be a nuclear fuel source for powering the spacecraft or for powering the craft on Titan. But how long do we expect it might live? What's the optimal time for the mission as of now?
So the plan is to use an MMRTG, right? So that's how we propose, and that's what the architecture is dependent on. And it will depend right now based on the cruise time that we're looking at. And we land and we have a 3-year prime mission, right? And throughout that whole prime mission, we have enough power, certainly, to do everything that we need to do. But we should keep getting enough energy out of the power source to keep going. And then over time, ultimately, it will start to degrade. But, we're looking at several years on the surface of Titan, even hopefully beyond the prime mission even.
Yeah, I mean, we're still learning, right, what we can do with these nuclear sources for spacecraft on planetary surfaces. Obviously, with like the Voyager spacecraft, they've been going for decades now, using a nuclear fuel source. And so it'd be cool if it could last for that long and really give us many years of measurements from the surface of Titan, and lots of really cool pictures and lots of really cool chemistry for all of us back here. I do want to change topics just a little bit. Before that, though, just remember for the audience, you can ask questions right now in SeganNet's chat feature at segannet.org or on the NASA Astrobiology Facebook page. I see questions coming in right now for Dr. Trainer, and so I'll get to your questions here very soon. But a few other questions I have first. So you've done a lot of other work, not just looking at Titan and its atmospheric chemistry and some of these things. You've also been involved with the SAM instrument on Curiosity, and you mentioned earlier like the methane detections on Mars. I remember when those first started coming out, and like Mike Mama was using a telescope here at Earth and looking at Mars and seeing methane, and a lot of people didn't believe it. I was skeptical of methane on Mars at first as well, but now we've had repeat measurements. But recently, you were also involved in an announcement of finding oxygen on Mars. And I wonder if you could just tell our audience about that detection and what we think might be going on to be putting both methane and oxygen potentially into Mars's atmosphere.
Sure. So we expected to find oxygen. Oxygen was measured certainly by the Viking landers as well as other spacecraft or other observations of Mars. So we knew that oxygen was there. What we were able to see with the SAM measurements that couldn't be seen before was how it changed over time, seasonally, and how it changed compared to the other major gases in the atmosphere. So with the SAM instrument on Curiosity, we've been on Mars for over 8 years. I have to pause because my daughter was born right after we landed. So I can always remember how long we've been there, how old she is. We've been on the surface for a long time. We're not making daily measurements of the atmosphere with the mass spectrometer, but we're making frequent measurements. And we were able to kind of build up over time coverage that then spanned all the seasons and had lots of points over repeated Mars years. And that was a big first, right? So all the other measurements had either been observations, from orbit or from telescope, or, for example, the Viking landers, which made that kind of comprehensive measurement of all the composition of the atmosphere, but only for a few sols, only for a few Mars days. So we sort of built up this first data set, and things like argon and nitrogen, which we know are inert. They don't chemically react to other species. They don't really interact very much with the surface. They behaved very well. It's a weird way to anthropomorphize them, but they have this very repeated cycle that we expected to see. And every year, we could fill in the points, and it would make this, put together this nice curve. But the oxygen was not following the same patterns. It would rise a lot earlier in the spring than the argon and nitrogen, and then it would kind of drop down really fast. And both of those aspects of the oxygen cycle were unexpected, based on what we know about oxygen photochemistry and the cycles in the atmosphere. You would expect it to actually mostly look like argon, behave like argon. So what it tells us, whenever we get to make a measurement that hasn't been made before, hasn't been made with the same resolution that it's been made before, and you don't see what you expect, it just means it's time to go back and question the assumptions. So we had an expectation based on only one real process of controlling oxygen in the atmosphere, which relates to photochemistry. And by seeing different behavior, it's telling us there's something else going on. And we don't have an answer yet. So these results took years and years to build up. And then we published them about a year ago. And part of the idea was to say, hey, this is an unprecedented data set. This is something interesting and new. And it was a little bit out to the community, the science community, maybe some of the people on this call, see what you can think about. I think that there's probably a really strong connection to the surface, to processes that are going on in the surface, heterogeneous chemistry. There may be a reservoir where oxygen gets converted into another species temporarily, and then it could be re-released. That's one way to potentially explain how it can kind of come out fast and then go back away fast. But we haven't found a smoking gun in terms of what would that reservoir be and what would trigger kind of release or reabsorption. We compared our results to everything else that we were measuring at the time, whether it was UV incidence, or temperature, pressure, surface, ground temperature, dust loading, the methane you measure. So we compared it as best as we could to the measurements of methane that were made. And the methane and oxygen, it's interesting. They sometimes follow each other and sometimes not. So there's parts of the year where they seem like they might be tracking, and then other parts where they're not. So that seems like another really important clue too.
Mm-hmm. Interesting. That's because it's really groovy. And so you guys heard it. Dr. Trainer has said it's a challenge. Help us figure out what's going on. Maybe someone listening right now, maybe an undergraduate student or high school student listening right now might be involved in helping us to solve these puzzles. And as always in science, it's not always a case of eureka. It's a case of, why is that happening? So Dr. Trainer, before I open it up to our audience questions, I do love for all of our guests just to chat a bit about what it is outside of science that drives your life forward. So you mentioned to me before that you're really into your family life, and you guys have a lot of hobbies together. You like to get outdoors with your family. I wonder if you could just let us know what kinds of adventures have you and your family been on lately?
Sure. Well, this has not been a normal year, as everyone can agree with. But a few years ago, we got really into trying to visit different national parks. I love the outdoors. I love the natural environment. I probably don't get into it as often as I would like, living in suburban Washington D.C. area. But we started trying to visit different national parks. The previous summer, we had gone to Shenandoah. We've been to some in Hawaii, like Haleakala. And I used to live in Colorado, so I've been to many of the parks in Colorado. But now my son, who's 11 now, he's like really into it. He wants to like be able to check some of these places off of his list. So this past summer, we were supposed to go to Yellowstone. We had to curtail those plans, but we decided to stay semi-local, and we made a visit down to Great Smoky Mountain National Park. And that was a first for all of us. It was amazing. It was beautiful. We loved it. We got to see some really cool wildlife, and it's just far away enough from where we are now. We really like birds. My kids like to do. They're not the most patient, quiet bird watchers, but when we do see new birds, we like to figure out what they are and kind of keep track, in a little book. And we saw some elk, again, park elk that were very blasé about the people and could care less about us there, not in any way afraid or interested. So that was really cool. And we also just tried to do, I think like a lot of people, we just tried to do some outdoor activities that seem safe, given trying to be careful with coronavirus. So we did horseback riding through the forest. I took my son zip lining through the trees, just lots of fun outdoorsy stuff. So a lot of what I do, the adventures I have are different than the ones I had before I had kids, but it's so fun as they get older, we can do more and more. And I can do fun things like zipline by conning my kid into doing it with me.
That's awesome. Yeah, my son's only 16 months old right now, and so I'm at that phase where he can't really do all the cool things I want to go do just yet. But so there is a hope that down the road we'll be going some ziplining together. I love it.
Yeah.
Sure. So I'm going to open it up now to the audience Q&A. We have a bunch of questions coming in from the audience. Keep those questions coming, folks. We'll try to get to all of them if we can. The first one is a question that came to us through Twitter. From a longtime watcher of the show, Dr. Jim Pass. As an astrosociologist, he says, he's interested in hearing your thoughts about the search for extraterrestrial life and how it affects societies even without ambiguous evidence, and how things might change if we do find such evidence.
Wow. That's a great question. I'm very much out of my expertise, and I'm speaking only. This opinion is only my own type answer. I think that if we are to discover life off of Earth, whether it's like something that presents itself to us or something even just as simple as a microbe that we discover on another planet, I'm hoping that will be very unifying for our society. It's a little bit of like the Star Trek view, I think. It really helping us remind ourselves as humans and as Earthlings how we're so much more similar than we are different. And I would like to think that would kind of bring us together as a species on Earth. And I think even for those of us who do search for life off of Earth, we have to think really hard about what could it look like? Should we expect it to be similar to life on Earth? And that already kind of puts you in that mindset and really thinking about what does it mean to be life on Earth? What does it mean to be an Earthling? What does it mean to be a citizen of this planet versus what could it be like for someone on another planet? So that is based on zero research. But my hopes, I think, of why part of why the search for life, I think, is an important endeavor for humanity and makes me hopeful for our society.
That's great. Yeah, I agree. I love that response. And our questions coming from our audience can be about all kinds of topics that they want to ask an astrobiologist. The next two questions are Titan related, though. So the first is from Andrew Planet. He asked on Twitter, was that very short active lifespan of the Huygens spacecraft intentional? Did they know it was going to last for such a short period of time?
Yes, absolutely. So it was designed to be a descent probe. So the whole mission for that Huygens probe was to fall through the atmosphere, and it did exactly what it was supposed to do. And in fact, the 70 minutes it survived on the surface was complete bonus science. Right. So that wasn't even originally planned because they couldn't guarantee what it would land in. Mm-hmm. So one thing you learned, what I'm learning, right? So this is the first time I've ever sat on a mission from the conception, all the way through development. And what I'm learning is you want to be really careful. You can't put requirements on the planet. So I can't guarantee Titan is going to cooperate. I can only plan for what I can constrain properly and what I can expect. And then there's some things where you're like, well, if Titan cooperates, we'll get this or this will happen, but we don't know.
Awesome. Yeah. So it could have just like sunk down into a goop of hydrocarbons and that could have been it.
or hit a harder surface than we expected, maybe, and broke something,
Mm-hmm. Oh, interesting. Yeah. So another question from Azul Pinoba on Twitter. Azul wants to know, is it known how Titan's seasons influence the methodological cycle?
It is, yeah. So one thing to keep in mind is that a year on Titan is the same as a year on Saturn, which is about 29 and a half Earth years. So Cassini was able to observe Saturn and Titan kind of going through a big seasonal change, right? But not even a whole year, only a half of a year. And so we were able to make lots of observations with Cassini flybys about how the seasons can shift some of the chemical species. We think it can influence, perhaps there's lakes near the sort of what look like dried out lake beds that may get filled if there's some rain in other seasons. And then just the rain in general is expected. We can see clouds that formed in sort of certain seasons in certain locations, but then not in others. So there's definitely expected to be an influence. It's very slow moving compared to Earth, not just because of that. Well, there's that long timeline of the seasons, but also just it's very cold. And so in general, the atmosphere is going to be a lot slower and a lot more sluggish than what we experience on Earth, right? The huge temperature gradients you can get from solar insolation on Earth, you're very far out there. The sunlight is going to just influence things in a smaller and slower way. And I should also say it's not just Cassini that helps us observe how Titan is evolving through the seasons. Of course, there's still ground-based or other space telescope measurements that can be made as well that help us track all those things. But so I would say I think we have a beginning understanding of how that works, and that's supported. Ongoing work on that also gets supported by models that we can do, sort of global circulation models that help us try to understand it and match the data. But with Dragonfly sort of will be a ground truth for at least this one area of Titan, making observations and really help us understand that even better.
And that's a great point too. Actually, there's another question right now from Anurup Mahanti at Astrobiologist on Twitter. He wants to know about the landing site selection, which we didn't even talk about yet. He says for NASA's Perseverance rover, we used remote sensing data of Mars to select a site of scientific interest, but also, the engineering had to allow us to actually have a landing site. So can you speak to what we currently have for a landing site for Dragonfly and how we selected it?
Sure, absolutely. So we have all the data that was accumulated from Cassini. So I mentioned sort of between the visual spectroscopy and radar data, we actually have a good set, and we picked locations on Titan where there was a good data coverage, so that we had the best data that we could have about what the surface was like. We have what we know from the Huygens probe coming in and taking up close images of the surface. And then we took that information, and then we also thought about, well, what do we want the mission to do, right? One of the biggest goals is to visit more than one type of compositional area. So one thing that we can see with the measurements we've been able to make of the whole Titan globe is we can't tell exactly what the surface composition is in every location, but we can classify it, right? So we can classify there's sort of like these dark areas. And then there's we got like blue areas where we know there's water ice included, and maybe some brownish or greenish, just classifying it all and looking at that, you can see how diverse the surface is. And so I talked a little bit about dunes, and I talked about impact craters. So in addition to being, topographically diverse, or geographically diverse, these are also chemically diverse areas, right? They have different provenances, so the materials are likely made of different things. And so we wanted to be able to visit as many of those places as possible, and to include one of these frozen over impact areas where we know there used to be liquid water, because that sort of gets at our prebiotic chemistry goals. And so we found this location near Selk crater. Selk is a known impact crater, and it's right near this Shangri-La area, right with the dunes. And so by going to this location, we're able to visit the dune fields, understand the organic sands that comprise them, where they come from, but then also look at an impact crater where there might have been this more advanced synthesis. And the data that we have isn't as high resolution as the type that we have for Mars, certainly, especially for, a Perseverance. We have very high resolution data for Mars, but you have to remember, we don't have to drive across the surface. And another cool thing is that when we come in, the craft itself comes out of the back shell and transitions to its own powered flight. And so it can pick its landing site, its initial landing site. And it does so with, using imagery and LiDAR and like terrain navigation to select a safe landing site. So it's okay that we don't know the exact precise, really, really high resolution areas. We know enough to know that there are big flat areas in these dunes, and that there's a lot of potential landing sites. And then as we go, we'll always be doing reconnaissance. We call it leapfrog. We'll always be flying over a new area, making really high detail, making our own maps, right? Coming back to the original landing site, deciding where the next target is, and then moving over to that.
Oh, awesome. And you kind of alluded to this earlier a good bit, but Miriam Nassim on SegaNet wants to know, from an astrobiology perspective, if you think Titan may be habitable or could be inhabited, and what kind of life you think might actually be able to survive on Titan.
Yeah, so this is such a fun question. The subsurface ocean, right, that's often thought about as probably the most likely long-term habitat for life, water-based life, right? Because if it's maintained for a long period of time, and if there's sufficient nutrients and gradients in that location, then that would be the place that would be most likely to harbor life. That's one reason we think about connection between that ocean and the surface as being really critical. But the truth is, we don't really know how life evolved on Earth, right? So maybe some of those surface environments, even if they're transient surface environments of liquid water, or if they're fed from the interior, it's possible that life could have at least persisted for brief periods of time in those environments. And I think Graham used the word like refuges or oases, maybe. And so maybe they would have been temporary, but 1,000 years doesn't seem temporary to like a bacteria, right? So it doesn't even seem temporary to me. That's a potential. Maybe it was just this very brief moment of time. And then if you want to get really exciting, then we can think about, okay, well, we know there's these methane and ethane seas at the poles. We know there's, maybe methane soaked sands in other places. And then we can start, having fun thinking about like weird life and what potential, other biochemistries could be supported in that type of environment. I know there's some good, some people have started looking into that type of possibility.
It's so groovy. Yeah, I remember a few years ago, the folks at Goddard's visualization studio released like this video of a submarine going down into one of Titan's lakes and looking around. Made me wonder if there could be some weird alien octopus that lives in methane and ethane lakes and super cold temperatures down there to grab that submarine.
Yeah. I think we all hope if we send a submarine anywhere, whether it's Titan or Europa, I think we all hope it'll get eaten by an octopus. As long as
exactly. Yeah.
Sure it does.
From Jules Verne, like it's just in all of our heads. It's ingrained in the culture of science fiction and all these things. So let's jump ship a little bit. Our next question comes from Blake Overbay on Facebook, Blake is majoring right now in environmental chemistry and has interest in abiogenesis and the origin of life. And so Blake wants to know, and you may not have the best answer for this. It's up to you how you want to answer it. If astrobiologists right now are trying to answer these questions of the origin of life, is there a lot of call for origin of life research? And do you think that we're getting closer to finding life from non-life?
We're closer than we ever were. That's the best answer I give. No, there's a huge community of people in origin of life research. Absolutely. I luckily before the shutdown happened, I was able to go in person to a really great meeting on origin of life research earlier this year, and there are so many different ways that question is being approached. It's very multidisciplinary. Philosophically, just, like a wide range of sort of philosophies of how to think about it. We're thinking about what happens if you bring in material from outside to a planet. What happens if the planet sort of makes its own, chemistry, kind of like I've been talking about with like the Titan, like prebiotic chemistry. There's so many different ways to think about it and to understand what are the controlling parameters of an environment. And people are making a ton of progress in understanding sort of what are those first critical steps of synthesis, at least for the early Earth. And so in that case, we have minimal constraints. And so it's good that so many people are kind of approaching it and thinking about it in different ways, because you have to explore all these potential pathways for how it might have happened on Earth. We have very little evidence of what happened back then. All we have is the endpoint, right? Mm-hmm. The life we see around us. But that's one thing why we think it's so cool to go to Titan too, because that's a place where you don't have life all over everywhere, right? Biology hasn't just overprinted on all of the chemical processes that are going on. And that's part of helping us, ultimately go back and think about what happened on Earth billions of years ago that led to the formation of life there.
Yeah, I often tell people that there's a good chance we'll never know for sure how life started here on Earth, because we might have lost that record chemically. But with Titan, there's a chance we could actually see the process in action, even if that process does take a very long time. So that's really cool to think about. Another question from another undergraduate, Kennedy Marthaler, has said that they're an undergraduate majoring in physical sciences, math and physics, and are determined to go to graduate school for either astronomy or looking into astrobiology. And they want to know if you have any tips in how to get started in such programs. They are, competitive sometimes to get into these programs. Mm-hmm. And so we can also go a little bit broader if you don't mind. What would your advice be to any of our undergraduates right now who are watching and might be interested in pursuing astrobiology?
Sure. So I'll speak specifically to how I got into astrobiology and what I think was really helpful for me. And what it was to stay in a primary discipline. So instead of pursuing maybe a degree, a PhD that was just astrobiology or what I did is I stuck with chemistry, which I really liked. But that could be physics, it could be geology, it could be any of those things. So I kind of stayed in a core discipline, or more traditional, I should say, is what I'm saying, discipline. And then got involved in, taking classes that were related to astrobiology or having research or participating in meetings and seminars that were focused around astrobiology. But I was really glad that I maintained sort of that grounding in that other discipline. So I recommend thinking about which types of science you're really passionate about. And so many of them have a link to astrobiology. Like, that's what I love about astrobiology. It's so multidisciplinary, and that's what makes it so fascinating. And that's what helps us make progress, right? Like, I'm the only, I may be the only chemist that like works around me at all in my group at NASA. And so I work with a bunch of people who all bring some other, sort of expertise in terms of their training. But then together we can make connections, and we can come together and kind of build something like that. So that's the advice I usually give.
Awesome. Yeah. And I noticed in your bio, so I'm a past AbGradCon organizer when we had it at CU Boulder in 2016. We just had our last episode of Ask an Astrobiologist was focused on AbGradCon and the importance of things like this, like, meetings and conferences where, undergraduates and graduate students and postdocs can come together and share their research. And you were a past organizer of AbGradCon, I saw. I wonder if you can speak to the importance of AbGradCon and other meetings and networking in your career.
Oh, absolutely. I would not have my job if it weren't for astrobiology meetings. Actually, when I think about it, one meeting, sort of AbSciCon meetings I would go to every time they happened. When I was a graduate student, I was very lucky. I had an advisor who really pushed me, pushed all of her students to present at meetings and get out there. And by presenting my research sort of on Titan, aerosols and early Earth aerosols, I made connections with one scientist who was very interested in working at Penn State at the time, and then remembered that discussion years later when she was in a group at Goddard that was wanted to hire somebody new. And that's who passed my name, for example, to the person who ended up hiring me in my current job. And in addition to that, when I organized AbGradCon, I did so with two other people, one of whom was a postdoc at Goddard. So when the job opportunity came up, I was like, oh, hey, Avi, there's a job opening. Do you think I should try? And if I come out to give a seminar, can I visit you and see how you like it and what your life is like at Goddard? And that was my first friend when I did
awesome.
take the job. And now it turns out both of the people I organized AbGradCon with, we all work at Goddard, all three of us.
Awesome. Yeah. So, I became the host of this show because of AbGradCon and meeting Sanjoy Sam and the folks who run Blue Marble Space and SaganNet and becoming friends. And it led to me being here now, too. So that's wonderful. There's one more question that just came in that I really want to ask because it's a really cool question. Going back to Titan, can Titan, so you mentioned how Titan has this bedrock of water ice, and we've discussed, this sand particles of organic material. So user @RogueZebraTMR on Twitter wants to know, can Titan have different types of rocks? Could it be like, we have igneous, metamorphic, sedimentary rocks. Are we also categorizing rocks, that this icy material on Titan in the same way?
So we will. I think. I really believe we will. At one of our earliest Science 2 meetings, we talked about how we're going to be sort of writing the mineralogy of Titan with the kind of studies that we can do with Dragonfly. And I think knowing what we do know now, I have every expectation that we'll find evidence, right, of sedimentary formations, but it'll be made of things that are affected by liquid methane flowing over them instead of liquid water flowing over them, right? We expect to find maybe even conglomerates of like water ice chunks, but maybe they're an organic matrix or vice versa. And we know we have like these impact melts and so I think absolutely we're going to be classifying all the materials that we find, and it's going to be a lot of parallels because that's how we study other planets, right? We take what we know from Earth and we apply it to those other systems.
Awesome. Do you have time for one more question, Dr. Trainer? Yeah. Okay, awesome. So one more question, and to all of those asking questions, thank you very much. We're not going to get to all of them, obviously, but I do appreciate everyone asking your questions for Dr. Trainer. Our last question comes from Azul again. She wants to know, in terms of resistance design, how does the Dragonfly spacecraft differ from the Huygens spacecraft, allowing it to have that much longer of a lifespan?
Oh, it's power. It's 100% power. So the Huygens probe was powered with a battery. And so eventually the battery just runs out. It's whereas, as we talked before, the idea is that Dragonfly was designed to be powered with a nuclear energy source that can last much longer for years and years.
Well, that's wonderful. Well, Dr. Trainer, thank you so much for joining us for Asking Astrobiologist. I'm way more hopeful now about Dragonfly. I'm so excited for this mission. There's so much more to learn. So hopefully folks can reach out to you if you're okay with that. You are @planet_trainer on Twitter, and I think folks can find you there and ask more questions. And thank you for joining us for Asking Astrobiologist.
Thank you so much. This was so fun.
Well, it was great having you. For everyone watching, if you're interested right now, our producer and director, Mike Toillion, is going to put up a poster from NASA of the Dragonfly mission. And you can download and print this special Dragonfly mission poster for yourself. The link is now available at the NASA Astrobiology Twitter account. That's at NASA Astrobio, no space, obviously. And so for everyone watching, everyone asking questions, getting involved, thank you so much for asking an astrobiologist. And as always, stay curious.